Before we begin, thank you so much for being here. If you enjoy calm science stories like this, it really helps when you like the video, subscribe to the channel, and share it with someone who might fall asleep to it too. Your support lets me keep making more quiet documentaries like this one. I'm also really curious about you. What time are you listening right now, and where are you? Are you at home in bed on a late bus studying or just winding down after a long day? Let me know in the comments. With that, let's drift back in time and explore what Earth was like in the Precambrian world. The story of the Precambrian world begins around an ordinary-looking star that forms inside a spiral arm of the Milky Way galaxy when swirling clouds of gas and dust collapse under their own weight and flatten into a thin rotating disk. In this disk, most of the material gathers into a central glowing ball that becomes the young sun, while the remaining dust and ice grains circle around it in countless small clumps. Over long spans of time, these clumps collide, stick, and grow, forming larger and larger bodies that continue to sweep through the disk. One of these growing bodies gathers enough mass to pull in more material by gravity and slowly becomes the early Earth, a world that is at first just one of many forming planets, but that will later record an unusually complete history of rock and water. At the same time, other planetary embryos develop on nearby orbits, their paths sometimes crossing in slow but powerful collisions that reshape their surfaces and interiors. In this crowded setting, the early Earth is not yet the stable planet with familiar continents and oceans. Instead, it is still forming, still gaining heat from each impact, and still surrounded by debris that has not yet fallen into planets been thrown out of the system or spiraled into the sun. This stage of planet building does not leave many direct traces in rocks, but the physics of how disks behave and how planets grow makes it likely that the young Earth passes through a sequence of very energetic events. One important event is the impact that leads to the formation of the Moon. Models of orbit's angular momentum and rock behavior at high temperature suggest that a body roughly the size of Mars collides with the growing Earth at an oblique angle. Much of the impacting body and part of Earth's outer layers are heated and partly vaporized, and a mix of rock droplets and vapor is launched into orbit around the planet. This material gathers into one large companion that becomes the Moon, while the rest falls back and adds further heat to the outer layers of Earth. The newly formed Moon orbits much closer to Earth than it does today, so it looks far larger in the sky and raises strong tides in the early oceans that will appear later. Even without direct rock samples from this earliest time on Earth, the chemistry and isotopic composition of moon rocks, as well as the way the Moon orbits, support the idea that Earth and Moon share a linked violent beginning. In terms of formal geological time, almost all of this early story sits inside what later geologists called the Precambrian, a broad span that covers nearly the first 4 billion years of Earth history before the familiar fossil-rich rocks of the Phanerozoic begin. The Precambrian itself is divided into 3 great eons. The Hadean eon marks the earliest phase when planet building and intense bombardment dominate and when surfaces may be repeatedly melted or buried. The Archean eon follows when the planet cools enough for stable crust, widespread oceans, and a persistent atmosphere to exist, even though conditions are still very different from those of later times. The Proterozoic eon comes after that, with more stable continents, long-lived oceans, and progressive changes in atmosphere and life that moved the planet toward the boundary with the Cambrian period. In everyday life, these names may seem abstract, but in geology, they mark real and measurable shifts in the character of rocks, in the chemistry of minerals, and in the types of microfossils and structures that appear in the record. When geologists speak of the Cambrian boundary, they refer to a point in the rock record about 540 million years ago where a particular set of fossil-bearing layers begins to appear around the world. Layers below this level belong to the Precambrian, while layers above belong to the younger Phanerozoic eon. From a time perspective, the familiar slice of Earth history that includes forests, dinosaurs, mammals, and humans occupies only the last small part of the younger eon, while the long stretch of the Precambrian covers the far greater part of the record. Thinking about this distribution of time helps explain why the Precambrian world is both distant and central. It is distant because it lies far back along the timeline at intervals measured in billions rather than millions of years. It is central because during that long span, the solid Earth, the oceans, the atmosphere, and the earliest forms of life all arise and slowly change into more complex systems. The outer context for the Precambrian is therefore set by this contrast between a young sun and a still-forming planet. The sun at this stage is slightly fainter than it is today, emitting less total energy while the early Earth rotates faster with shorter days and nights and wears a surface that is still responding to the last stages of bombardment. Around them, the rest of the solar system also settles as the last large impacts become less frequent. Smaller bodies are cleared from many orbits, and the gas that once filled the disk is blown away into interstellar space. What remains is a planetary system that looks broadly similar to the present one, with rocky planets in the inner region, giant planets, and icy bodies further out, and countless smaller objects following paths that sometimes cross the orbits of the larger worlds. Within this setting, Earth enters the long Precambrian span with a specific mass composition and distance from the Sun. These starting conditions decide how much heat is stored inside the planet, how strong gravity is at the surface, and how much energy arrives from sunlight. Together, they frame the next layers of the story in which the behavior of an extremely hot young planet, the pattern of impacts, and the rotation rate shape the earliest conditions at the surface before a stable crust and oceans appear. In the Hadean eon, the young Earth is still shedding the energy of its birth, and the planet behaves in ways that differ strongly from the quieter world that follows later. Much of the interior remains very hot, warmed by the decay of short-lived radioactive elements and by the repeated conversion of impact energy into heat. Large bodies continue to strike the surface, sometimes arriving at speeds of many kilometers per second, and each major collision delivers enough energy to melt rock on a regional or even global scale. After the giant impact that produces the Moon, the outer layers of Earth are at least partly molten, forming what geophysicists call a magma ocean, a deep layer of mobile, partially or wholly liquid rock that extends from the surface down into the mantle. In such a state, any solid crust that tries to form is easily broken or recycled, and convection within the molten layer moves heat rapidly from the deep interior toward the surface. The top of this magma ocean loses heat efficiently to space, especially where it is exposed directly. But even once a thin, fragile crust begins to form, cracks and volcanic outpourings open new pathways for heat to escape. The surface is not uniform. Some regions may be capped temporarily by cooling rock, while nearby areas remain molten or semi-molten, and the pattern changes over time as impacts, convection, and cooling interact. This continuous adjustment gives the early planet a restless skin that does not yet behave like the stable plates seen in later geological periods. Above the magma ocean, the early atmosphere is also shaped by high-temperature processes. Volatile substances, such as water carbon compounds and sulfur gases, are released from the interior through widespread volcanism, and additional material may arrive on impactors that contain ice and carbon-rich minerals. At the same time, the intense heat at the surface can drive some of these components into a temporary rock vapor atmosphere after the largest impacts, especially in the immediate aftermath of the collision that forms the Moon. As the surface cools between such events, heavy rock vapor condenses or falls back, while lighter gases persist as a thick, dense, and likely greenhouse-rich envelope. This atmosphere is frequently disturbed by the mechanical effects of impacts that punch through it, by plumes of hot gas and debris launched upward, and by the exchange of material between the molten surface and the air. Little direct record of these earliest atmospheres survives because later geological recycling destroys or overprints almost all Hadean rocks, but models constrained by present-day volcanic gases, by the chemistry of meteorites, and by high-pressure experiments give a range of plausible compositions. These typically involve high levels of carbon dioxide, water vapor, and other greenhouse gases, very low free oxygen, and a surface pressure that may be significantly higher than today. The planet's rotation during the Hadean is also faster than in later times. After the impact that creates the Moon-Earth completes one spin in a period that may be closer to a dozen present-day hours than to a full present-day day, although the exact value is uncertain. This rapid rotation affects the shape of the planet, making it slightly more flattened at the poles and more bulging at the equator than it is now, and it influences how heat and material move in the interior and atmosphere. The nearby Moon raises strong tides in any surface magma or in early bodies of water that later condense, and even before stable oceans exist, this gravitational interaction between Earth and Moon transfers angular momentum and slowly lengthens the day. Over tens of millions of years, the Moon's orbit gradually expands, the strength of tides decreases, and the rotation of Earth becomes less rapid. But during the Hadean, the combined system is still in a relatively compact configuration. Inside the planet, the contrast between the hot, possibly partially liquid mantle and the denser metallic core drives vigorous convection. Rising plumes of hot rock in the mantle and sinking cooler material help even out temperature differences, while at the core boundary, the motion of conducting metal starts to organize into patterns that can support an early magnetic field. Evidence for such an ancient field comes indirectly from the magnetization of some of the oldest surviving minerals, which suggest that a geodynamo may operate even when the surface is still hostile. A magnetic field at this stage would help deflect some charged particles from the young sun, which is more active than at present and emits a stronger solar wind. This, in turn, may reduce the rate at which the upper atmosphere is stripped away, allowing more of the gases supplied by volcanism and impacts to be retained. The balance between internal heat surface cooling and incoming energy from the sun therefore controls how long magma oceans can persist, how quickly early crust can appear, and how thick and stable early atmospheres can become. Over time, the largest impacts become less frequent as remaining planetesimals are either accreted by planets ejected from the system or collide with the Sun. Smaller impacts continue, but their energy is no longer sufficient to remelt the entire surface. As a result, the pattern of global scale melting gives way in stages to a more patchy and complex surface where some regions can remain solid for longer intervals. Even so, during much of the Hadean Earth is best described as a hot, dynamically evolving world whose outer layers are locked in a cycle of heating, melting, and cooling, driven by both interior processes and external bombardment. The conditions created by this interplay set the groundwork for the next major transition in which the magma oceans retreat, the rate of giant impacts falls, and more durable crust can survive long enough to influence how the first long-lived surfaces and later oceans take shape. As time passes, after the most intense phase of accretion, the balance of processes at Earth's surface begins to shift from repeated global melting towards slower cooling and partial preservation of solid rock. The rate of giant impacts declines because many of the larger planetesimals that once crowded near Earth's orbit have already been swept up, scattered, or destroyed. Smaller impacts still arrive and can locally melt or fracture the crust, but they no longer erase the entire outer shell as often as before. At the same time, radioactive heat from short-lived isotopes decreases as those nuclides decay away and the mantle loses energy through vigorous convection and volcanic activity. Together, these changes allow parts of the outermost layer to remain solid for longer periods so that the first, more durable crust can form and survive. This earliest crust is likely dominated by dark, dense, magnesium-rich rocks, similar to present-day basalt and related compositions, because the magma, ocean, and early mantle are still very hot and tend to produce melts of this type. Where these melts erupt or intrude near the surface and then cool, they create a patchwork of solidified plates and fragments that may be broken up by later events, but that still mark an important transition. The surface is no longer entirely molten. Instead, it consists of regions of solid rock separated by zones of strong volcanism and deformation, and the average thickness of the crust gradually increases. Evidence for this stage is scarce because later tectonic and metamorphic events recycle most of the original rocks, but a small number of very old mineral grains, especially zircons found in younger sediments, preserve chemical signals that point back to early crustal processes more than 4 billion years ago. These zircons record conditions that imply the presence of relatively cool, chemically evolved crust and perhaps even interaction with liquid water, although the exact environments remain debated. Their existence shows that in some places, Earth's surface had already moved beyond a purely basaltic shell and was starting to generate more silica-rich rocks that are the precursors of continental material. As the crust thickens and becomes more complex, the pattern of convection in the mantle beneath it adjusts. Hotter, buoyant regions of mantle rock rise toward the base of the crust, where they may partially melt and feed further volcanism, while cooler, denser regions sink back into the deeper interior. This circulation transports both heat and material-moving compatible elements and volatiles through the system. Volcanoes and widespread fissure eruptions release large amounts of gases into the overlying atmosphere, including water vapor, carbon dioxide, nitrogen, and sulfur-bearing species. These gases do not all arrive at once. Instead, they are delivered over long intervals as magma ascends, crystallizes, and exsolves volatiles, and as impactors add their own cargo of ices and carbon-rich compounds. The result is a gradually thickening atmosphere that is dominated by greenhouse gases and is largely devoid of free oxygen. High levels of carbon dioxide and water vapor help retain heat from the faint young sun, compensating for the lower solar output and limiting how much the surface cools. At the same time, the continuing decline in average impact energy and the growing stability of the crust make it easier for low-lying basins and depressions to persist without being immediately erased. This geological relief sets the stage for the first long-lived surface reservoirs to form when conditions allow water to condense at the surface. In many models, clouds and rainfall become more common as the surface and lower atmosphere cool. But the exact timing distribution and amount of early precipitation remain uncertain because direct sedimentary records from the Hadean are almost entirely absent. What is more secure is that by the time the Archean eon begins around 4 billion years ago, Earth supports a crust that is recognizably divided into stronger and weaker regions, with some domains thickened enough to behave as buoyant continent-like nuclei. These proto-continents are likely composed of more silica-rich rocks such as tonalite, trondhjemite, and granodiorite, which are produced when basaltic crust is partially melted under appropriate pressure and temperature conditions. Their lower density compared with the surrounding mafic crust makes them more resistant to being recycled into the mantle, so they begin to persist as long-lived blocks floating on top of the convecting interior. Around and between these early continental seeds, broad areas of oceanic-type crust continue to form at spreading centers or other zones of upwelling mantle. The tectonic style during this time is still a subject of active research. Some models propose that a form of plate tectonics already operates, with subduction of dense lithosphere and lateral motion of plates, while others suggest that the lithosphere behaves more like a stagnant or sluggish lid with episodic overturns. In either case, the observable outcome at the surface is a mixture of old and new crust, with some fragments surviving many cycles of heating and deformation, and others being rapidly reworked. As more crust stabilizes, erosion and weathering also start to play a larger role. Even before large continents rise high above sea level, any exposed rocks at the surface experience mechanical and chemical breakdown. Under the influence of temperature changes, possible rainfall, and interaction with the atmosphere, particles and dissolved ions are transported into low-lying areas where they can accumulate as sediments. These early sediments, though mostly destroyed or transformed later, begin the long history of material being moved from high to low regions and trapped in layers that can later record conditions at the time of their deposition. The combined effect of these processes is that during the late Hadean and early Archean Earth transitions, from a state dominated by global-scale melting and resurfacing to a state dominated by a more permanent, rocky shell, the crust is thicker, more differentiated, and mechanically stronger than before. The atmosphere is denser and more chemically complex, maintained primarily by continuous volcanic outgassing, rather than by transient rock vapor after impacts. Large impacts still occur, but rarely have the energy to reset the entire system. Instead, they reshape limited regions and interact with a surface that now has enduring basins, rising protocontinents, and a developing pattern of tectonic and erosional processes. This more stable outer shell defines the physical framework on which later oceans' climates and the earliest surviving surface environments are established. As Earth's outer shell becomes more stable and the rate of giant impacts continues to fall, conditions at the surface reach a point where liquid water can collect and persist, and the first long-lived surface oceans begin to form. The sources of this water lie both inside and outside the planet. Some fraction is held within the minerals that make up the building blocks of Earth and is released gradually as the mantle melts and volcanic activity brings deep material toward the surface. Another fraction may arrive on bodies that contain ice and hydrous minerals, such as certain types of asteroids and comets, which strike the planet during and after the main phase of accretion. Measurements of hydrogen and other isotopes in present-day seawater in mantle-derived rocks and in primitive meteorites suggest that no single source can explain all of Earth's water. Instead, the planet likely receives a mixture of contributions with interior water released by outgassing and external water delivered during collisions, both playing roles over long spans of time. Whatever the exact proportions by the transition from the Hadean into the Archean eon, there is enough water at or near the surface for a global-scale hydrosphere to exist. Once volcanic gases supply large amounts of water vapor to the atmosphere and the surface cools to suitable temperatures, this vapor can condense into clouds and fall as rain. At first, the rain returns to a still hot and rugged surface where pools and thin films of water may flash to steam or react chemically with newly formed rocks. As cooling progresses, more of this precipitation can gather in low-lying regions, forming lakes, seas, and eventually a connected global ocean that fills the deeper basins of the crust. The timing of this transition is difficult to fix in detail because the rock record from these earliest times is sparse. However, the chemistry of ancient zircons older than 4 billion years hints that liquid water interacts with crustal material even during parts of the Hadean, while the presence of well-developed sedimentary rocks and pillow-like volcanic structures in Archean terrains supports the existence of standing bodies of water by early in that eon. These clues do not give a full picture, but they indicate that Earth's surface water system is already active long before familiar continents and life-filled shorelines appear. The first oceans differ in several important ways from modern seas. The heat flowing from the interior is higher, so seafloor volcanism and hydrothermal activity are more intense. Fresh crust is generated at elevated rates, and hot fluids circulate through newly formed rocks, exchanging chemicals between the solid earth and the water that percolates through fractures and porous layers. At the same time, the atmosphere above the ocean is dense and rich in greenhouse gases, such as carbon dioxide and water vapor with little or no free oxygen. The young sun emits less total energy than it does today, so without strong greenhouse warming, the surface would likely be frozen. Instead, the combination of atmospheric composition and internal heat keeps at least much of the ocean in a liquid state, even though exact average temperatures remain uncertain. Some models propose that early oceans may be relatively warm, while others allow for cooler conditions with local or episodic ice cover. The available evidence from ancient oxygen isotopes in minerals and from the types of sediments preserved does not yet yield a single agreed value for early ocean temperature, but it is consistent with liquid water being widespread. The chemistry of the first oceans is also distinct. With no extensive land plants and soils, and with a different balance of gases in the air, the rates and types of weathering reactions are not the same as those of later times. Volcanic gases add large amounts of carbon, sulfur, and chlorine-bearing species to the system, and hydrothermal vents on the seafloor release dissolved metals and silica. In the absence of significant free oxygen, many dissolved iron species remain in reduced, more soluble forms, so iron can be transported through the water column in higher concentrations than in present oceans. Sodium and chloride ions, which make up most of the salt in modern seawater, are still present, but their exact concentrations may change over time as weathering, hydrothermal exchange, and mineral precipitation proceed. Suspended particles from volcanic eruptions, impacts, and erosion of early crust give the waters a high load of fine material, which settles out to form layers of muds and chemical sediments on the seafloor. The surface of the ocean interacts closely with the atmosphere above it, exchanging heat gases and water vapor. Evaporation transfers energy from the surface into the air, while condensation in clouds releases that energy higher up and returns water to the ocean or to exposed land through rainfall. Winds, driven by differences in temperature and pressure, push surface waters into currents that move heat horizontally across the planet. The pattern of these currents is affected by the faster rotation rate of Earth, which strengthens the Coriolis effect and may organize large-scale flows differently from today. Tides raised by the nearby moon are stronger, and in shallow seas, or along the edges of early crustal blocks, they can generate significant mixing and transport of sediments. Even in the absence of complex shorelines, this interaction between tide, wind, and rotation helps stir the upper layers of the ocean and spread dissolved substances and heat. In low-lying regions, where crust stands above sea level, rainfall and small streams begin to erode rocks and carry material toward the sea. This process is initially limited by the modest height and aerial extent of early land, but it still marks the beginning of a surface water cycle that links atmosphere, land, and ocean in a continuous loop. Over time, this cycle will play a central role in controlling climate and in transporting nutrients and chemical species that influence later biological activity. During the early stages, however, its main observable effect is to produce a growing variety of sediments. Some are made of fragments of pre-existing rocks, while others precipitate directly from seawater as dissolved components reach saturation and crystallize. Together, they create layered deposits on the ocean floor that, when preserved, provide one of the few windows into surface conditions on the young planet. From a planetary perspective, the appearance of long-lived oceans marks a major change in how Earth stores and moves energy and material. A global ocean acts as a vast heat reservoir, smoothing out temperature differences between day and night and between equator and poles more effectively than a bare rock surface could. It also offers a medium in which dissolved substances can be transported, mixed, and reacted on time scales that are short compared with those of deep geological change. In the Precambrian world, this new layer of liquid water sits between the still active interior and the evolving atmosphere, mediating exchanges among them. The establishment of this hydrosphere completes the basic outer framework of the system within which later variations in atmosphere and climate crustal-style chemical cycles, and eventually surface habitats will develop and leave their imprints in the rock record. With a long-lived ocean now in place and a more stable crust beneath it, the next layer of the Precambrian story lies in the state of the air and the balance of light and heat reaching the surface, especially during the Archean eon. The young sun at this time shines with less power than today. Stellar models and observations of similar stars at different ages show that the sun's luminosity several billion years ago is significantly lower, perhaps by around 1/3 compared with its present value. Less energy arrives at the top of Earth's atmosphere, so if all other factors were the same, the surface would tend to be colder, and large parts of the oceans might freeze. Yet geological evidence from Archean rocks does not point to a planet locked in permanent deep freeze. Instead, many lines of evidence suggest that liquid water is common and that sediments are deposited under conditions that are not dominated by thick global ice. This apparent mismatch between a faint young sun and signs of relatively mild surface temperatures is known as the faint young sun problem, and it directs attention to the composition and behavior of the early atmosphere. The air during the Archean is very different from the familiar modern mixture. Free molecular oxygen is either absent or present only in tiny amounts. Instead, the atmosphere is dominated by gases released from the interior and from reactions at the surface. Volcanic outgassing contributes large quantities of water vapor, carbon dioxide, and nitrogen, along with smaller amounts of methane, ammonia, hydrogen, and sulfur, bearing species such as hydrogen sulfide and sulfur dioxide. The exact proportions and changes over time are not fully known, and they are still the subject of active research. But broad ranges can be constrained by the chemistry of ancient rocks, by models of mantle composition, and by the need to maintain surface temperatures consistent with a liquid ocean. A thick blanket of greenhouse gases provides the most straightforward way to keep the Archean surface warm under a faint sun. Carbon dioxide strongly absorbs outgoing infrared radiation, and in high enough abundance, it can raise the equilibrium temperature of the lower atmosphere. Water vapor also acts as a potent greenhouse gas, but its concentration depends on temperature and the presence of liquid water. Methane produced by volcanic processes and by certain microbial metabolisms once life is established is even more efficient at trapping infrared radiation. In an atmosphere with very little oxygen, methane can reach higher concentrations than in the modern world before being destroyed by photochemical reactions, so it may play an important role in warming. Nitrogen, which is chemically less reactive under these conditions, likely accumulates as a major background gas, increasing the overall surface pressure. Higher total pressure enhances the greenhouse effect of other gases by broadening their absorption lines and can also influence the behavior of clouds. At the same time, the interaction between incoming ultraviolet light from the sun and the mix of gases in the upper atmosphere may produce organic hazes. In some models, an atmosphere rich in methane and carbon dioxide under strong ultraviolet irradiation can generate complex hydrocarbon aerosols that coagulate and form a high-altitude haze layer. Such a layer can reflect some incoming sunlight back to space, cooling the planet, but it can also absorb ultraviolet radiation and re-emit energy at longer wavelengths, with net effects that depend on particle size thickness and vertical distribution. The balance between greenhouse warming and haze-induced cooling might shift over time as volcanic outgassing rates, methane production, and solar output change. Direct evidence for the composition of the Archean atmosphere is limited because air itself does not fossilize. Instead, geologists infer atmospheric states from proxies preserved in minerals and rocks. For example, the presence of detrital grains of minerals that are easily oxidized, such as uraninite and pyrite in ancient river and delta deposits, implies that these minerals could survive transport at the surface without being converted to oxide forms, which suggests low levels of free oxygen. Sulfur isotope patterns in Archean sediments show mass-independent fractionation, a signature that arises when sulfur-bearing gases are exposed to ultraviolet light in an atmosphere with little oxygen and no significant protective ozone layer. This pattern fades after the rise of oxygen in the Proterozoic, supporting the idea that the Archean air is largely anoxic. The absence of extensive carbonate platforms in the oldest rocks, and the characteristics of those carbonates that do exist, put constraints on carbon dioxide levels, though the exact range remains debated. Other proxies, such as the ratio of certain trace elements or the presence of specific weathering profiles, add additional pieces to the puzzle. The climate system linking this atmosphere to the oceans and surface is active and variable, but generally avoids extreme long-term states of full glaciation during much of the Archean. Regional or episodic ice may form at high latitudes or altitudes, especially if greenhouse gas concentrations fall or if volcanic aerosols temporarily dim sunlight. But there is little clear evidence for global-scale ice cover in this early eon. Instead, many Archean sedimentary sequences show structures that are consistent with liquid water environments, such as shallow marine shelves, tidal flats, and deep basins. These include cross-bedding, ripple marks, graded bedding, and other features formed by currents and waves. Together, they point to oceans that are at least seasonally ice-free over large areas. The distribution of land also affects Archean climate. Early continental fragments are relatively small and low-lying compared with later continents. So the capacity of land to reflect light, store heat, and influence atmospheric circulation differs from that of the modern world. With less exposed land, the ocean covers a larger fraction of the surface, smoothing temperature contrasts and moderating climate. Weathering of silicate rocks on land removes carbon dioxide from the atmosphere over long times by converting it into carbonate minerals that are buried in sediments. In the Archean, if land area is reduced, this sink may be weaker, allowing carbon dioxide to remain in the air at higher levels for a given volcanic input, which in turn favors a warmer climate. However, seafloor weathering, hydrothermal alteration, and other processes also consume carbon dioxide, and their combined effects must be weighed to understand the net balance. Clouds form where moist air rises and cools, and they both reflect incoming sunlight and trap outgoing infrared radiation. The properties of Archean clouds are difficult to reconstruct, but they are controlled by the same basic physics as later clouds modified by different aerosol populations and temperature structures. With a fainter sun, small shifts in cloud cover could have substantial effects on climate. Modeling work explores how combinations of carbon dioxide, methane, nitrogen pressure, and clouds can produce surface temperatures consistent with geological observations, but multiple solutions remain possible and uncertainties in key parameters persist. What emerges clearly, however, is that the Archean atmosphere is not a thin, passive shell. It is a thick, chemically active layer that plays a central role in keeping the surface within a range that allows liquid oceans to persist under reduced solar input. Energy from the sun enters mainly in visible and near ultraviolet wavelengths, is absorbed by land and water, and is re-emitted as infrared radiation. Greenhouse gases intercept some of this outgoing energy and redirect it, raising the temperature of the lower atmosphere and the surface. Volcanic eruptions and meteor impacts inject particles and gases that can temporarily modify this balance, while the slow evolution of the sun's luminosity and Earth's internal heat flux shifts the baseline over hundreds of millions of years. Within this framework, the Archean atmosphere and climate provide a dynamic but broadly stable outer environment. They determine the range of temperatures and chemical conditions at the air-sea interface and at the surface of emerging land, which in turn control rates of weathering patterns of sediment deposition and the availability of certain compounds. These, together with conditions in the ocean interior and at the seafloor, define the next inward region of the Precambrian system, in which the character of Archean oceans and their diverse habitats comes into focus. In the Archean world, once a global ocean has formed and the atmosphere has settled into a broadly stable but anoxic state, the interior of the ocean and the habitats along the seafloor become the next important layer of the system. The ocean at this time likely covers a larger fraction of the planet than it does today, because continental areas are still limited to scattered, relatively low-lying crustal blocks. Wide expanses of deep water separate these early fragments of land, and much of the seafloor consists of young, dark volcanic rock produced at zones where hot mantle material rises and melts near the surface. Heat flow from the interior is higher than in later eons, so seafloor spreading and volcanism are correspondingly more vigorous. New oceanic crust forms rapidly moves away from upwelling centers and is altered by interaction with seawater, before eventually returning to greater depth in whatever tectonic style operates. Even if plate motions are not yet organized into the clear patterns seen on the modern Earth, the basic processes of upwelling, melting, and crustal creation are active and supply a continuous input of heat and material to the base of the ocean. This elevated heat flux shapes both the physical structure and the chemical character of Archean seawater. Where magma approaches the surface beneath the seafloor, it heats the surrounding rocks and any water that circulates through fractures. Cold seawater percolates down into the crust, warms, reacts with minerals, and rises again as buoyant hydrothermal fluid. At vents on the seafloor, these hot fluids discharge back into the ocean, carrying dissolved metals, reduced sulfur, silica, and other components that they have leached from the rock. When they mix with colder ambient seawater, minerals precipitate and form chimneys, mounds, and diffuse flow fields. Although the exact composition of Archean hydrothermal systems is not directly observable, the chemistry of altered oceanic rocks and the presence of certain ore deposits in ancient greenstone belts show that intense water-rock interaction at elevated temperature is widespread. In deep basins far from land, the water column is stratified by temperature and density. Warm surface layers receive sunlight, wind mixing, and direct exchange with the atmosphere, while deeper layers are cooler, darker, and more isolated from rapid change. With little or no oxygen supplied at the surface, the deep ocean remains largely anoxic, meaning that free oxygen is absent as a dissolved gas. In such conditions, reduced forms of iron and other elements stay in solution more easily than in later oxygen-rich seas. So deep and mid-depth waters can carry significant loads of dissolved iron and manganese. Vertical mixing by currents, internal waves, and episodic overturns redistributes these constituents and slowly transports heat from the interior of the planet toward the surface. The exact temperature profile of the Archean Ocean is still debated, with some lines of geochemical evidence interpreted to suggest relatively warm average temperatures and others favoring cooler conditions. But most scenarios agree that the ocean is not uniform. Local environments near hydrothermal vents, volcanic centers, and upwelling zones differ strongly from broad open ocean regions, and shallow coastal shelves have different physical regimes again. Near the surface, interaction with the atmosphere controls gas exchange and sets key chemical boundaries. Carbon dioxide from the air dissolves into the upper ocean, where it forms a suite of carbonate species whose balance depends on temperature, alkalinity, and pressure. In the absence of extensive land plants and soils, alkalinity is supplied mainly by weathering of exposed rocks and by hydrothermal processes, rather than by thick river systems running off large continents. If total alkalinity is high enough in certain regions, carbonate minerals such as calcite and dolomite can precipitate and form chemical sediments. Archean carbonate platforms and stromatolitic buildups in some sequences record periods when such precipitation is active in shallow, sunlit waters. Elsewhere, where silicic acid concentrations are high due to hydrothermal input, silica may precipitate as chert-forming layers and nodules within sediments. In the deeper parts of the ocean, fine particles settle from the water column and accumulate on the seafloor. These include fragments of volcanic ash, tiny pieces of eroded crust carried by currents, and chemical precipitates formed higher in the water column. With no large plants or animals to stir the sediment, early seafloor deposits are shaped mainly by physical processes such as gravity flows, turbidity currents, and bottom-hugging density currents generated by variations in salinity or particle load. Over time, these processes create thick successions of fine-grained mudstones, sandstones, and chemical layers that can later be compressed, deformed, and metamorphosed into the rocks now seen in Archean terrains. The interfaces between different depositional environments, such as the transition from deep basins to shallow shelves or from open ocean to restricted lagoons, generate characteristic patterns in the sediments, including graded beds, cross-stratification, and ripple marks. Their presence in ancient rock packages allows geologists to reconstruct aspects of Archean ocean structure even though the original water is long gone. Around the margins of early crustal blocks, water depths are shallower and the influence of tides and waves is stronger. The nearby moon, still closer to Earth than it is today, raises tides that can be large in amplitude, especially in enclosed or narrowing basins where resonances amplify the motion. These tides, together with wind-driven waves, rework sediments on continental shelves and coastal plains, producing tidal flats, sandbars, and channels that migrate over time. Each tidal cycle moves water back and forth, alternately exposing and flooding low-lying surfaces. Over long periods, this repeated movement imprints a rhythmic structure on the sedimentary record and mixes chemical species between the ocean and any ponds or lagoons that fringe the land. Shallow subtidal zones beneath the constantly moving water are bathed in light, receive a steady supply of dissolved components from both the open ocean and local runoff, and experience moderate physical disturbance. These properties make them important sites for chemical reactions, and once life arises, biological activity. In contrast, deep ocean floors far from land receive less detrital input from weathering and erosion, so their sediments are more strongly influenced by what falls out of the water column and by hydrothermal precipitates. In some settings, the repeated alternation of iron-rich and silica-rich deposits over long intervals records changes in the relative balance of hydrothermal fluxes, seawater chemistry, and perhaps the redox state of portions of the ocean. Such alternations are a key feature of banded iron formations that become more prominent later, but have roots in Archean seafloor processes. The positions of upwelling zones where deep waters rise toward the surface are tied to patterns of wind stress rotation and basin geometry. Where these upwelling currents intersect the surface, they bring nutrient-rich and chemically distinct waters into contact with the atmosphere and sunlight. Even before complex ecosystems fill these regions, they are significant because they enhance gas exchange and control how reduced species are oxidized or preserved. The overall circulation of the Archean Ocean is governed by the same physical principles that control modern ocean currents, including the effects of planetary rotation density gradients and basin shape. But the details differ because of the different distribution of land, the stronger internal heat flux, and the distinct atmospheric composition. Without large polar ice caps, and with a different arrangement of continents, latitudinal temperature gradients may be smoother, and some circulation patterns could be simpler or more symmetric than in the present. Yet local variations remain important, especially near active volcanic centers and along the edges of crustal blocks, where steep temperature and chemical gradients exist over relatively short distances. Taken together, these features make the Archean Ocean a complex three-dimensional environment in which heat and material are constantly redistributed between the deep interior and the surface. The seafloor from hydrothermal vents in the deepest basins to wave-work shelves at the edges of early land provides a wide range of physical and chemical conditions. Some regions are hot, chemically reducing, and rich in dissolved metals and gases, while others are cooler, more slowly changing, and dominated by gradual accumulation of fine sediment. This diversity of settings forms the immediate context for later chemical cycles and for the earliest traces of life that become visible in the rock record, even though at this stage the description remains focused on the structure and behavior of water and rock rather than on the detailed nature of any organisms that may occupy these habitats. As the Archean eon advances, the crust that once forms as thin, mostly basaltic sheets above a hot convecting mantle begins to organize into more persistent and more varied structures. Heat flow from the interior is still high, but it is lower than in the earliest stages, and the rate of giant impacts has fallen enough that no external event routinely melts the entire surface. Under these conditions, some parts of the crust can survive for long intervals without being returned wholesale to the mantle. Within this evolving shell, chemical and physical processes start to separate lighter components from denser ones, and this separation slowly produces patches of crust that are thicker, less dense, and more silica-rich than the surrounding mafic rocks. These patches form the nuclei of the earliest continents. The generation of this buoyant continental crust involves repeated melting intrusion and metamorphism. Basaltic rocks formed at the surface or near surface are buried by new volcanic additions or by tectonic thickening, and as they descend into hotter regions of the crust and upper mantle, parts of them begin to melt. The melts that rise from this partially molten source are enriched in silica and certain incompatible elements, because these components prefer to enter the melt rather than stay in the solid residue. When such melts reach higher levels and crystallize, they form rocks similar to tonalite, trondhjemite, and granodiorite, which have compositions intermediate between basalt and granite. Over time, repeated episodes of melting and intrusion build composite bodies of these lighter rocks. Because they are less dense than the mafic crust and mantle that surround them, they tend to float higher and resist recycling, becoming long-lived blocks that rise above the average level of the seafloor. These blocks do not at first resemble the broad, stable continents familiar from later times. Instead, they are smaller, more irregular, and fringed by zones of intense deformation and volcanism. Their surfaces are shaped by erosion, by volcanic resurfacing, and by the constant action of waves and tides along their margins. Their interiors are subject to episodes of heating and deformation as new intrusions force their way in, as nearby crust thickens or thins, and as the underlying mantle flow patterns evolve. Nevertheless, viewed over long spans of time, they mark the emergence of a distinct class of crustal material that is thicker, older, and more chemically evolved than the oceanic crust that continues to form elsewhere. Surrounding and threading between these early continental blocks are belts of strongly deformed volcanic and sedimentary rocks that geologists call greenstone belts. The name comes from the common presence of green-colored minerals such as chlorite and actinolite, which form during metamorphism of basaltic and ultramafic rocks. In cross-section, many greenstone belts show a layered architecture with thick sequences of basaltic lava flows, including pillow lavas that indicate eruption underwater, interleaved with volcanic fragmental rocks, chemical sediments, and clastic sediments derived from erosion of nearby high ground. Some belts also contain distinctive rocks called komatiites, which are high magnesium lavas formed from very hot mantle melts. These rocks are far less common in younger crust and are a marker of the higher mantle temperatures of the Archean. The arrangement of rock types within greenstone belts suggests that they record ancient oceanic basins, volcanic arcs, back arc environments, and related settings where crust is added and deformed along zones of convergence and extension. In many regions, greenstone belts lie between or around older, more silica-rich crustal blocks and are themselves folded, faulted, and metamorphosed. The contacts between belts and neighboring blocks are often steep, and the structures within them indicate that large horizontal and vertical movements have occurred. These relationships have led many researchers to interpret greenstone terrains as relics of an early form of mobile tectonics, in which crustal fragments move, collide, and stack, even if the precise mechanisms do not match those of modern plate tectonics in every detail. Within these belts, the physical conditions at the time of formation and later metamorphism can be read from mineral assemblages and from the deformation features locked into the rocks. High strain zones, shear fabrics, and recumbent folds point to intense compression and lateral transport, while metamorphic minerals record pressures and temperatures that range from those characteristic of shallow burial to those of deep crustal levels. In some places, the pattern of metamorphic grades suggests that blocks of crust are thrust over one another, creating thickened regions that later undergo partial melting and contribute more felsic material to the system. In this way, greenstone belts not only preserve evidence of Archean oceanic and volcanic environments, but also participate directly in the growth of continental crust. The tectonic style during this interval remains a matter of careful study and debate. Some lines of evidence support the view that a form of plate tectonics involving subduction of dense lithosphere and lateral motion of discrete plates operates at least intermittently. These include features that resemble accretionary wedges, arc-like volcanic assemblages, and paired metamorphic belts. Other observations are more consistent with episodic overturn or sagduction, where dense volcanic piles sink into weaker, hotter lower crust, while lighter material rises in response. It is possible that the planet passes through stages in which different behaviors dominate as the lithosphere strengthens and the mantle cools. Whatever the details, the outcome is a surface marked by repeated cycles of extension, thickening, and lateral transport that generate a mosaic of crustal fragments with varied histories. On the emerging continental blocks, surface processes begin to leave more complex signatures. Weathering of exposed rocks under the Archean atmosphere breaks down minerals and releases ions that rivers and surface runoff carry toward the sea. Even if the total land area is limited, this flux contributes to the chemistry of the early oceans and to the formation of sedimentary rocks along continental margins and in interior basins. Rivers carve channels and deposit sands and muds, while lakes and shallow inland seas accumulate finer sediments and evaporitic minerals where conditions allow. Tectonic subsidence creates accommodation space for these sediments, and later uplift and deformation may expose them again, stacking records of multiple cycles on top of one another. The first broad cratonic regions where thick, stable continental cores persist over very long times begin to form from these repeated episodes of magmatism, deformation, and sedimentation. A craton consists of a crustal portion made of ancient igneous and metamorphic rocks, underlain by a root of cool, thick lithospheric mantle that is stronger and more buoyant than the surrounding mantle. Once established, such roots are difficult to disrupt, so the overlying crust has an enhanced chance of survival through later tectonic events. In the Precambrian world, some of the oldest cratons preserve Archean greenstone belts and granitoid complexes in their interiors, surrounded by younger Proterozoic additions around their edges. These regions serve as archives for the earliest phases of continent building and tectonic organization. The growth of continental crust and the formation of cratons have important consequences for the rest of the Earth system. As continental areas enlarge and rise higher above sea level, they change the pattern of reflection and absorption of solar radiation, modify atmospheric circulation, and influence where rain falls and where runoff flows. Exposed land becomes a more significant site for chemical weathering of silicate minerals, which consumes carbon dioxide and fixes it in carbonate and clay minerals that may be transported to and buried in the ocean. This, in turn, can adjust atmospheric greenhouse gas levels over long time scales and feed back into climate. The distribution of continents also helps organize ocean circulation, guiding currents, shaping seaways, and defining the geometry of continental shelves where shallow marine environments develop. Within the crust itself, the assembly and breakup of larger land masses, sometimes approaching supercontinent scale during later parts of the Precambrian, rearrange the positions of continental blocks across different latitudes and longitudes. Although this supercontinent cycle becomes more clear in the Proterozoic, its roots lie in the Archean processes that first create and stabilize continental fragments. As these fragments drift, collide, and rift apart under the influence of mantle convection, they continually reconfigure the geography of land and sea. Each reconfiguration changes the locations of volcanic arcs, sedimentary basins, and mountain belts, which in turn alters patterns of erosion, sediment supply, and chemical exchange between crust ocean and atmosphere. By the later Archean, the surface of Earth consists of a patchwork of oceanic basins, volcanic arcs, greenstone-filled belts, and thickening continental blocks, all underlain by mantle that continues to convect and evolve. This crustal architecture defines the solid framework on which subsequent chemical cycles operate. It determines where elements are stored, how they are mobilized, and along which paths they return to the surface or are carried into the deep interior. With continents now rising more clearly above sea level and with greenstone belts recording the interaction of volcanic, sedimentary, and tectonic processes, the stage is set for tracing how key elements such as carbon, sulfur, iron, and oxygen move through the combined system of crust, ocean, and atmosphere during the long Precambrian eons. With continents beginning to rise higher above sea level and wide oceans covering most of the surface, the way key elements move between rock, water, and air becomes a central part of the Precambrian world. Among many elements, carbon, sulfur, and iron are especially important because they are sensitive to the chemical state of their surroundings and leave clear traces in the rock record. During the Archean and early Proterozoic eons, these elements cycle through the atmosphere, the hydrosphere, and the crust in patterns that reflect the absence of free oxygen in the air, the presence of a warm and often chemically reducing ocean, and the continued activity of volcanism and tectonics. These cycles do not yet operate in exactly the same way as they do in the modern world, but the basic idea of elements moving through reservoirs along a set of linked pathways is already established, and over long times these repeated transfers gradually alter both the solid Earth and the fluid envelopes that surround it. The carbon cycle in the Precambrian begins with sources that release carbon from the interior and from existing rocks. Volcanic outgassing at mid-ocean ridges at arcs and in intraplate settings brings carbon dioxide and smaller amounts of other carbon-bearing gases into the atmosphere and the ocean. Metamorphic reactions that heat carbonate-bearing rocks or buried organic material release additional carbon dioxide and methane. These inputs maintain a background level of carbon species in the air and water, because without them, the combined action of weathering and burial would gradually deplete the accessible carbon pool. Once in the atmosphere, carbon dioxide dissolves into the surface ocean, where it forms a mixture of dissolved carbon dioxide, bicarbonate ions, and carbonate ions. The relative proportions of these species depend on temperature, alkalinity, and pressure. In regions where the product of calcium or magnesium with carbonate ions reaches saturation, carbonate minerals such as calcite and dolomite can precipitate. In the Archean and early Proterozoic, Such precipitation occurs widely in shallow marine settings on the flanks of early continents and volcanic platforms forming carbonate shelves and platforms that later may host stromatolitic buildups and other structures. When these carbonates accumulate and are buried, they act as a long-term sink for inorganic carbon. At the same time, weathering of silicate minerals on land consumes carbon dioxide as it converts calcium and magnesium-bearing silicates into clays and dissolved ions that are transported to the ocean and eventually fixed as carbonates. On a planetary timescale, this silicate weathering feedback helps regulate atmospheric carbon dioxide because higher temperatures and higher carbon dioxide tend to accelerate weathering, which in turn draws down carbon dioxide. In the Archean, this feedback operates in a context of limited continental area and strong seafloor alteration, so seafloor weathering and hydrothermal reactions also play major roles in consuming carbon dioxide. The balance between volcanic outgassing, silicate weathering on land and seafloor, and carbonate burial sets the long-term level of atmospheric carbon dioxide and thus influences climate. Evidence for the behavior of the carbon cycle in the Precambrian comes from carbon isotope ratios in carbonate and organic matter preserved in ancient rocks. Small but systematic differences between the isotopic composition of carbonates and coexisting reduced carbon phases indicate that some carbon is partitioned into reduced forms and removed from short-term exchange, while the remaining carbon cycles between atmosphere and ocean. These patterns show that a recognizable carbon cycle with sources sinks and internal fractionation is present even when the atmosphere is anoxic, and the biosphere, though not yet discussed in detail here, is dominated by microscopic forms. The sulfur cycle during the Precambrian is likewise linked to volcanism, seawater chemistry, and redox conditions, but it shows distinctive features that reflect the low oxygen content of the air. Volcanic gases contain sulfur mainly in reduced and moderately oxidized forms, such as hydrogen sulfide and sulfur dioxide. When these gases enter the atmosphere and hydrosphere, they undergo a series of reactions that depend strongly on the presence or absence of oxidants and on the intensity of ultraviolet radiation. In an atmosphere with very little oxygen and no substantial ozone layer, ultraviolet light penetrates deeply and can drive unusual photochemical reactions among sulfur-bearing species. The products of these reactions include a variety of sulfur isotopic signatures that are not mass-dependent in the way seen in younger rocks. When sulfur from this atmospheric pool is deposited as sulfate or sulfur containing aerosols and later incorporated into sediments, it carries this distinctive isotopic pattern. At the same time, dissolved sulfur species in the ocean participate in reactions at the seafloor and within sediments. In anoxic Archean seawater, the overall concentration of sulfate, the oxidized form of sulfur that is abundant in modern oceans, is thought to be low because there is little oxygen to convert reduced sulfur into sulfate on a large scale. Instead, much of the sulfur in the ocean is present as reduced species, either as dissolved hydrogen sulfide or as sulfide minerals such as pyrite. Hydrothermal vents on the seafloor contribute reduced sulfur directly, and reactions between these sulfur species and dissolved metals form sulfide minerals that precipitate near vents or within the upper layers of the crust. In some environments, microbial processes likely enhance the reduction of sulfur and the formation of pyrite. But even without focusing on biology, The rock record shows that Archean sediments contain significant amounts of sulfide minerals, indicating that reduced sulfur is a major component of the system. The presence of both mass-independent sulfur isotope signals from the atmosphere and mass-dependent fractionation patterns from low-temperature processes within sediments allows reconstruction of how sulfur moves between atmosphere, ocean, and crust through time. The iron cycle in the Precambrian ocean is perhaps the most visually striking in the rock record because it produces banded iron formations and other iron-rich deposits that stand out in ancient strata. In a world with almost no free oxygen in the atmosphere, iron released from the mantle at mid-ocean ridges and volcanic centers enters the ocean mainly as ferrous iron, a reduced and relatively soluble form. Hydrothermal fluids leach iron from mafic and ultramafic rocks and deliver it to seawater along with silica and other components. In the deep anoxic parts of the ocean, this ferrous iron can remain in solution, transported over significant distances by currents. Where these iron-rich waters encounter more oxidizing conditions, for example, near the interface between deeper anoxic waters and shallower regions that receive some oxygen or other oxidants, ferrous iron is converted to ferric iron, which is less soluble and tends to precipitate as iron oxyhydroxide particles. These particles settle to the seafloor and can form laterally extensive layers of iron-rich sediment. In many Precambrian sequences, iron-rich layers alternate with layers dominated by silica, forming the characteristic banded appearance of banded iron formations. The silica-rich bands may form from direct precipitation of silica from seawater that is supersaturated due to hydrothermal input, while the iron-rich bands reflect intervals when conditions favor rapid oxidation and precipitation of iron. The detailed causes of the alternation in thickness and frequency of bands remain under study and may involve a combination of changes in hydrothermal flux basin circulation and local redox state. What is clear is that these deposits require an ocean that can carry large amounts of dissolved ferrous iron and an environment that allows periodic or spatially restricted oxidation and precipitation. The combined carbon, sulfur, and iron cycles interact in several ways that shape the Precambrian surface environment. Burial of reduced carbon and reduced sulfur in the form of organic matter and pyrite removes electrons from the surface system, while weathering of these same phases in later times returns them. The relative rates of outgassing, weathering, and burial help determine the overall redox balance of the atmosphere and ocean, even in the absence of significant free oxygen. Iron acts as an additional redox buffer because the conversion between ferrous and ferric forms can store or release oxidizing power. In an Archean setting, where the atmosphere remains largely anoxic and the deep ocean is reducing, much of this buffering occurs within the ocean and sediments rather than in the air. Over long intervals, shifts in these cycles change the distribution of carbonates, iron formations, and sulfide-rich strata in the rock record. By tracking these changes, geologists can infer how the chemical environment of the surface evolves during the Precambrian. The patterns that emerge from such studies show that the cycles of carbon, sulfur, and iron are not static. They respond to variations in tectonic activity, in the intensity and location of volcanism, in the growth and erosion of continents, and in the exchange between deep and shallow ocean waters. Within the framework of a still anoxic atmosphere and a reducing ocean interior, these cycles define the chemical background against which later biological activity becomes visible and against which later changes in atmospheric composition will stand out. At this stage, however, the focus remains on their role as interconnected pathways that move key elements between crust water and air, gradually modifying the planet's surface reservoirs, while preserving their history in the layered rocks of Archean and early Proterozoic terrains. As the physical and chemical structure of the Precambrian Earth settles into oceans, continents, and active element cycles, traces appear in certain rocks that point to the presence of life. These traces are small, often subtle, and preserved only in rare fragments that survive billions of years of deformation, metamorphism, and erosion. They consist of tiny carbon-rich particles, layered sedimentary structures, and specific isotope patterns in minerals, all of which are examined carefully because non-biological processes can sometimes produce similar features. The earliest such evidence comes from very old rocks in a few ancient terrains, such as those in southwestern Greenland and in parts of Western Australia and southern Africa, where Archean and even late Hadean crust has escaped complete destruction. In these regions, bands of metamorphosed sedimentary rocks, known as supracrustal belts, contain layers that once were muds, sands, and chemical precipitates on or beneath the seafloor. Within some of these layers, geologists find concentrations of carbon that differ in isotopic composition from the inorganic carbon of associated carbonates. Carbon has two stable isotopes that are commonly measured, a lighter and a heavier form, and biological processes tend to incorporate slightly more of the lighter isotope into organic matter. When such organic matter is buried and preserved, its isotopic signature can remain detectable even after the original cells and tissues are destroyed. In certain ancient rocks, older than 3.5 billion years, the carbon in small graphite particles appears to be enriched in the lighter isotope in a way that resembles the pattern produced by biological carbon fixation. This observation suggests that by the time those sediments were deposited, some form of carbon-based life may already be present and active at Earth's surface. However, because high-grade metamorphism can also redistribute carbon and potentially alter isotope ratios, each claim of very early life based on graphite isotopes is examined critically. Researchers compare multiple lines of evidence from the same rocks, including their depositional setting, mineral associations, and thermal history, to determine whether a biological origin remains plausible after all non-biological alternatives are considered. In some cases, the combined data support a biological interpretation, while in others, the origin remains uncertain. Alongside isotopic clues, there are physical structures in ancient sedimentary rocks that resemble microbial mats. Microbial mats are layered communities of microorganisms that grow on surfaces in shallow water environments. Even in the absence of detailed cellular fossils, the behavior of such mats can leave distinctive sedimentary features. For example, mats can bind and trap fine particles, stabilizing them against erosion and causing them to build up into thin laminae. They can also cause the surface of soft sediments to wrinkle, crack, or form small domes as the mat grows and responds to changes in water level currents and sediment supply. When these structures are buried and lithified, they form characteristic textures that can be recognized in cross-section. In Archean rocks, from regions such as the Pilbara Craton in Australia and the Barberton Greenstone Belt in South Africa, columnar and domal laminated structures interpreted as stromatolites, appear in carbonate and siliciclastic sequences more than 3 billion years old. Stromatolites are layered sedimentary buildups, often domed or columnar, formed by the interaction of microbial mats with their environment. In modern settings, they grow in shallow sunlit waters, where waves, tides, and currents deliver fresh sediment that sticks to the sticky surfaces of microbial communities. Over time, repeated cycles of binding, trapping, and mineral precipitation build up centimeter to meter scale structures with fine internal lamination. The occurrence of similar laminated domes and columns in Archean rocks indicates that complex layered microbial communities inhabit shallow marine environments by that time. In some localities, these stromatolitic structures occur in association with other features consistent with an intertidal or subtidal setting, such as ripple marks, desiccation cracks, and tidal bedding rhythms, strengthening the interpretation that they represent biological activity in nearshore environments. Microscopic examination of some Archean rocks reveals additional potential microfossils. These take the form of small, rounded, or filamentous carbon-rich structures that resemble cells or filaments of simple microorganisms. In ancient cherts, which are fine-grained silica, rich rocks that can preserve fine detail, such structures have been reported with ages around 3.5 billion years. Their sizes and shapes fall within the range of known bacterial and archaeal cells, and some occur in clusters or arrangements that are suggestive of colonies or filaments. As with isotopic evidence, these claims are carefully scrutinized because purely chemical or physical processes can sometimes produce carbon-rich spheres or filaments that mimic biological forms. Researchers evaluate whether the structures are indigenous to the rock or introduced later, whether they are associated with sedimentary features indicative of a surface environment, and whether their internal organization is consistent with known microfossils from younger rocks. In some cases, the evidence supports a biological interpretation, while in others, uncertainty remains, and the features are described as possible or putative microfossils rather than definitive ones. Beyond visible textures and shapes, the geochemical environment recorded by Archean sediments often points to the presence of localized microscale habitats. Fine layering in shallow water carbonates and silts, combined with indicators of repeated wetting and drying, suggests that surfaces such as tidal flats, lagoons, and the tops of submerged banks experience frequent fluctuations in temperature, salinity, and water depth. These conditions would naturally create numerous micro-niches, where films of water, thin sediments, and interfaces between oxidized and reduced chemical species coexist over small distances. Even in an overall anoxic world, small zones near the sediment surface and in the upper water column could maintain distinct chemical conditions supporting gradients in pH redox state and nutrient concentration. Such gradients are important because many energy-yielding reactions, whether biological or purely chemical, rely on the movement of electrons or ions down potential differences. The sedimentary record indicates that such gradients exist in Archean environments, for example, where iron-rich deeper waters meet shallower regions with different chemical conditions, or where hydrothermal fluids mix with ambient seawater near the seafloor. In these mixing zones, minerals precipitate in distinctive patterns and layered chemical deposits form. Within pore spaces of sediments and in the fine cracks and voids of rocks, fluids circulate and interact with minerals over very small scales, providing surfaces for adsorption and microenvironments that remain protected from large-scale physical disturbance. While these features do not by themselves prove the presence of life, they show that the physical and chemical setting is rich in microscale structures where any existing organisms could live, attach, and influence local reactions. The rock record from the late Archean and early Proterozoic becomes richer in such indications. Stromatolites appear in more varied settings, including extensive carbonate platforms along the edges of growing continents and in shallower interior seas. Their shapes diversify with cones, columns, and branching forms all represented. Some successions show repeated stacks of stromatolitic layers interbedded with fine clastics and chemical sediments, implying that layered microbial communities are able to re-establish themselves after episodic burial by storms or longer-term shifts in sea level. In places, fine lamination preserves small-scale irregularities that resemble trapped grains and shrinkage cracks in matte surfaces. Carbon isotopes from these rocks continue to show the characteristic offset between inorganic carbonate and reduced carbon that arises when a portion of carbon is fixed into organic matter and later buried. Together, these lines of evidence indicate that by the late Archean microbial life is not limited to isolated niches, but is widespread in shallow marine environments and influences sedimentary processes over broad areas. Even as attention focuses on these shallow and near-shore settings, there are signs that life, if present, may also inhabit deeper parts of the ocean and the rocks below the seafloor. Certain Archean and early Proterozoic hydrothermal deposits, including some sulfide-rich ores, show textures and isotope patterns that suggest low-temperature alteration of minerals in the presence of fluids that have interacted with organic matter or experienced biological sulfur processing. The exact nature of such interactions is often uncertain, especially after later metamorphism, but they are consistent with the idea that microscale habitats extend into the subsurface, where fluids circulate through fractures and porous zones in hot chemically reactive crust. In modern settings, such environments host diverse microbial communities, and although no direct fossils of such communities are preserved from the Archean, the combination of geological and geochemical clues points toward a similarly complex, though microscopic, biosphere. Throughout this interval, the limitations of the rock record and the possibility of non-biological explanations for some features require that interpretations remain cautious. For each claimed early fossil or biosignature, alternative pathways for its formation are considered, including purely inorganic precipitation, metamorphic segregation of carbon, or abiotic synthesis of organic compounds. In many cases, especially for the very oldest rocks, the passage of time has caused such extensive recrystallization and deformation that the original textures are difficult to read, and debates continue about how to interpret them. Nevertheless, when multiple independent lines of evidence from different locations point to similar patterns, such as isotopically like carbon in ancient sediments, stromatolitic structures in shallow water deposits, and consistent carbon isotope offsets between carbonate and reduced carbon through long intervals, it becomes increasingly difficult to explain all observations without invoking some form of early life. In this way, the microscale traces preserved in Archean and early Proterozoic rocks, although incomplete and sometimes ambiguous, collectively build the case that the Precambrian Earth hosts a biosphere dominated by microbial communities. These communities occupy surfaces, sediments, and perhaps subsurface habitats, and they leave behind a layered legacy of textures and chemical signatures. At this stage of the narrative, the focus remains on the physical record of these communities embedded in the rocks rather than on the detailed inner workings of the cells themselves. But the evidence is sufficient to show that microscopic life has become a persistent component of Earth's outer environment long before complex organisms appear. In the Precambrian world, the rocks show that microscopic life is present and widespread, but the inner workings of those cells do not fossilize in the same way as shells or bones do in younger rocks. Instead, the main clues to what early organisms are doing come from chemical patterns that they leave behind in minerals, sediments, and dissolved substances. These patterns are the indirect imprint of metabolism, the set of chemical reactions that cells use to gain energy and to build their structures. In an environment where the atmosphere lacks free oxygen and the oceans are largely reducing meaning that many elements exist in forms that can still accept electrons, the most successful metabolic strategies are those that tap into steep chemical gradients between reduced and more oxidized compounds. The planet provides these gradients in many places, such as where hydrothermal fluids mix with seawater, where deeper anoxic waters meet shallower layers influenced by light and the atmosphere, and where microbial mats trap and transform dissolved substances at the sediment surface. Within these settings, different groups of microorganisms specialize in distinct pathways, and although their cells are rarely preserved, the byproducts of their metabolisms accumulate over time and are recorded in the rocks. One major class of metabolisms in this early world is anoxygenic photosynthesis, a form of light-driven energy capture that does not release oxygen as a waste product. In contrast to later oxygen-producing photosynthesis, which splits water and produces molecular oxygen, anoxygenic photosynthesis uses other compounds as electron donors, such as hydrogen sulfide, ferrous iron, or molecular hydrogen. Microorganisms capable of this process live in the upper parts of the water column or on illuminated surfaces where they receive enough light, but still have access to reduced compounds from below. When these cells absorb photons, they drive the movement of electrons through internal pathways that create energy-rich molecules used to fix carbon dioxide into organic matter. The presence of anoxygenic photosynthesis in the Precambrian is inferred from several lines of evidence. In some ancient sedimentary sequences, the distribution of sulfur isotopes and the occurrence of certain sulfur-bearing minerals point to the repeated cycling of sulfur through reduced and oxidized states in shallow sunlit environments in a way that is most easily explained if light-driven sulfur oxidizers are present. In iron-rich basins, the association of iron formations with shallow water structures suggests that light may drive the oxidation of ferrous iron to ferric iron, either directly by photochemical reactions or indirectly through the activity of photosynthetic microbes that use iron as an electron donor. In both cases, the key point is that energy from sunlight is being used to move electrons from reduced species into more oxidized forms, creating chemical gradients that other organisms can exploit. Another important group of metabolisms in the Precambrian oceans is chemolithotrophy, in which microorganisms obtain energy by oxidizing inorganic compounds rather than relying directly on light. Chemolithotrophic cells live where reduced compounds such as hydrogen, hydrogen sulfide, ferrous iron, or ammonia are available often near hydrothermal vents in the subsurface or at redox boundaries in the water column and sediments. When they oxidize these compounds, they transfer electrons to acceptors such as carbon dioxide nitrate, or where available partially oxidized iron or sulfur species. The energy released by these reactions supports carbon fixation and cell maintenance. Hydrothermal systems in Archean greenstone belts and younger Precambrian terrains contain mineral assemblages and isotope signatures that indicate extensive interaction between reduced fluids and seawater at temperatures and conditions that are consistent with chemolithotrophic activity. For example, certain iron and sulfur-rich deposits show patterns of sulfur and iron isotopes that are difficult to reproduce solely by high-temperature inorganic reactions, but are readily produced when microbial communities repeatedly oxidize and reduce these elements at lower temperatures in the shallow crust or on the seafloor. Although it is often impossible to prove that microbes rather than abiotic processes control each specific case, the widespread occurrence of such signatures suggests that chemolithotrophic metabolisms are common wherever redox gradients exist. In parallel with these pathways, metabolisms that produce methane play a central role in the early biosphere. Methanogenesis. The biological production of methane is carried out by certain archaea that live in strictly anoxic environments. They use simple substrates such as carbon dioxide and hydrogen carbon monoxide, or small organic molecules like acetate, combining them in reactions that release methane and water and that provide enough energy for growth and maintenance. These organisms occupy niches in which other more energetically favorable electron acceptors are scarce, such as deep sediments, the interiors of microbial mats, and parts of the subsurface crust. Evidence for early methanogenesis comes from very light carbon isotope signatures in some methane-rich fluid inclusions, and from the isotopic composition of organic matter in sediments that appear to have formed under strongly reducing conditions. The carbon in biogenic methane is strongly enriched in the light isotope compared with the carbon dioxide from which it is derived, leaving a characteristic offset that can persist through burial and metamorphism. In addition, the presence of high inferred methane levels in models of Archean climate and atmospheric chemistry, needed to maintain surface warmth under a faint sun, is more easily sustained if a continual biological source of methane is available. Again, while the exact timing and intensity of methanogenesis remain uncertain, the combined geochemical and environmental context strongly suggests that methane-producing microbes are important members of Precambrian ecosystems. The cycling of nitrogen, an element essential for proteins and nucleic acids, also bears the imprint of invisible metabolisms. In an anoxic reducing world, much of the nitrogen in the atmosphere is present as molecular nitrogen, which is abundant but chemically inert. To become available to living cells, this nitrogen must be converted into more reactive forms, such as ammonium. Nitrogen fixation, the biological conversion of molecular nitrogen into ammonia, is a demanding process that requires specialized enzymes and a significant energy input. Isotopic ratios of nitrogen in some Archean and Proterozoic sediments indicate that by those times, biological nitrogen fixation is already operating. Because the patterns of enrichment and depletion seen in sedimentary nitrogen are consistent with known biological fractionation. Once fixed nitrogen is present, other microbial processes, such as nitrification and denitrification, can cycle nitrogen between oxidized and reduced states. Although these pathways depend on the local availability of oxidants and may be limited in a largely anoxic global environment. The net effect is that microbial communities participate actively in making nitrogen available and in redistributing it among different chemical reservoirs, even when the atmosphere itself remains mostly unchanged in its bulk composition. Many of these metabolisms operate together in layered microbial mats, which are common in shallow Precambrian environments. A typical mat may have a thin upper layer that is exposed to light during the day, and that contains photosynthetic microbes beneath which lie zones where oxygen, if produced, is quickly consumed, and conditions become anoxic again over a depth of only a few millimeters. In these deeper layers, sulfate reducers, methanogens, and other anaerobic microorganisms carry out their metabolisms using the organic matter and oxidized compounds produced above as substrates. The result is a vertical sequence of microenvironments in which different redox reactions dominate at different depths. Even if the global atmosphere contains almost no free oxygen, small amounts can exist in the immediate surroundings of photosynthetic cells for part of the day, only to be consumed rapidly by reactions with reduced iron sulfides and organic compounds. This tight coupling between production and consumption means that for long intervals, the chemical structure of the global ocean and atmosphere can remain reducing even while enormous numbers of individual redox reactions, many mediated by biology, are occurring near surfaces and interfaces. The evidence for such layered microenvironments comes from the fine lamination and wrinkled textures of stromatolites, from the distribution of minerals, such as pyrite, siderite, and carbonate within millimeter to centimeter scales in ancient sediments, and from modern analogs, in which similar structures are produced by living mats. Geochemical models that try to match the observed isotope patterns of carbon, sulfur, nitrogen, and iron in Precambrian rocks generally require that large fluxes of elements pass through biological pathways. Purely abiotic cycles tend to produce different magnitudes or directions of isotopic fractionation than those actually measured. When biological fractionation factors are included, the models more easily reproduce the observed combinations of isotope ratios, especially when they allow for spatially organized communities with multiple metabolisms interacting in series. At the same time, the rock record shows that these metabolic networks are robust to large-scale changes in tectonic and climatic conditions. Through episodes of increased volcanism, crustal reorganization, and shifts in ocean chemistry, the signatures of microbial processing persist, indicating that by the mid-Archean, the biosphere is a stable, if microscopic, component of the Earth system. These invisible metabolisms not only sustain the cells themselves, but also gradually alter the composition of surface reservoirs by moving electrons from reduced to more oxidized species and by sequestering reduced forms of carbon and sulfur in buried sediments. Over very long time scales, the cumulative effect of countless individual reactions shapes the chemical environment recorded in Precambrian rocks. From the point of view of the physical Earth, these metabolic processes are an additional set of pathways superimposed on purely geological cycles, modifying them, but still constrained by the same flows of energy and material that arise from the planet's interior heat and from sunlight. In this way, the early microbial world remains mostly invisible to direct observation, yet its presence is firmly recorded in the elemental and isotopic patterns that mark the rocks as they pass from the Archean into the Proterozoic eon. Over long spans of Precambrian time, the combined action of geological processes and invisible metabolisms gradually alters the chemical state of the surface environment, and one of the most important changes involves the behavior of oxygen. For much of the Archean eon, free molecular oxygen in the atmosphere and open ocean is extremely scarce, even though small amounts may form locally wherever light-driven metabolism split water or oxidize reduced compounds. In microbial mats, shallow surface waters, and thin films around mineral grains, oxygen can appear transiently and be consumed almost immediately by reactions with ferrous iron sulfides and reduced carbon. In this way, countless small redox cycles operate within a globally reducing framework, and their products are mostly confined to local scales. The rock record from this interval, with mass-independent sulfur isotope signatures and widespread evidence for reduced iron in sediments and hydrothermal systems, indicates that the atmosphere as a whole remains essentially anoxic. Yet, these micro-scale processes are not chemically neutral. They continually transfer electrons from reduced species into more oxidized forms and sequester reduced carbon and sulfur in buried deposits. Over hundreds of millions of years, the slow accumulation of these buried reduced phases acts as a long-term sink for electrons at the surface. At the same time, volcanic outgassing and metamorphic reactions continue to supply reduced gases and minerals that can consume oxidants, so the overall redox balance of the surface reflects the competition between these inputs and the net burial of reduced material. As the Archean transitions into the Proterozoic eon, the balance begins to shift. Evidence for this shift comes from several independent kinds of geochemical signals preserved in rocks of intermediate age. In some sedimentary sequences deposited near the end of the Archean, there are indications of brief regional episodes in which surface waters and perhaps parts of the atmosphere experience slightly higher oxygen levels than before. These include intervals where certain redox-sensitive trace metals, such as molybdenum and rhenium, become more concentrated in sediments in ways that suggest increased oxidative weathering on land and mobilization of metals in rivers, as well as subtle changes in sulfur isotope patterns. Such episodes are sometimes described as whiffs of oxygen, reflecting the idea that oxygenation may occur in fits and starts before any permanent change in the background state of the atmosphere. In these intervals, the activity of oxygen-producing metabolisms, likely including forms of oxygenic photosynthesis, that split water may briefly exceed the capacity of volcanic gases and reduced minerals to consume oxygen in some surface reservoirs, allowing small accumulations in nearshore waters and perhaps in the lower atmosphere. Despite these local and short-lived departures, the broader environment remains largely reducing until a more sustained transition occurs in the early Proterozoic. This larger change is often called the Great Oxidation Event, not because oxygen suddenly appears for the first time, but because the level of free oxygen in the atmosphere and surface ocean rises from near zero to a persistent, though still relatively low value. This transition unfolds over tens of millions of years, around the time 2.5 to 2 billion years before the present, and it is recorded in a coordinated set of changes in multiple geochemical proxies. One of the clearest signals involves the disappearance of mass-independent sulfur isotope fractionation from sedimentary rocks. As long as the atmosphere lacks significant oxygen and ozone, ultraviolet light can penetrate deeply enough to drive unusual photochemical reactions among sulfur-bearing gases, producing non-mass-dependent isotopic patterns that are later preserved in sulfates and sulfides. When oxygen accumulates and ozone forms, ultraviolet radiation at the relevant wavelengths is absorbed higher in the atmosphere, and these photochemical pathways shut down. The resulting sulfur cycle produces only mass-dependent isotope fractionation, similar to that seen in younger rocks. In the geological record, this change appears as a sharp decline and eventual absence of mass-independent sulfur signatures in sediments younger than a certain age, marking the point at which atmospheric oxygen levels rise enough to alter the photochemistry of sulfur on a global scale. Around the same time, other indicators show that the surface environment becomes more oxidizing. The abundance and distribution of redox-sensitive trace metals in marine sediments change in ways consistent with an increase in oxidative weathering on land. For example, increased delivery of certain metals to the ocean can occur when oxygen in rainwater and soil air enhances the breakdown of sulfide minerals and releases trace elements that rivers then carry to the sea. The appearance of detrital grains that are unstable in the presence of oxygen, such as uraninite and pyrite, becomes rare or disappears from river and delta deposits after this interval, suggesting that transport at the surface now takes place under conditions where such minerals are rapidly oxidized. In the rock record, this transition is also associated with the first widespread occurrence of red beds, sedimentary rocks, whose iron-bearing minerals are oxidized, giving them a characteristic reddish color. These deposits form on land or in shallow basins under an atmosphere that contains enough oxygen to convert ferrous iron to ferric iron during weathering and early diagenesis. Together, these observations indicate that following the Great Oxidation event, the surface air and at least the upper parts of the ocean contain enough free oxygen to cause major changes in how various elements behave. The accumulation of oxygen does not necessarily require a change in the basic physics of the planet, but it does imply a rebalancing of sources and sinks in the global redox budget. On the source side, oxygen-producing metabolisms, especially oxygenic photosynthesis, generate molecular oxygen as a byproduct of splitting water. The fundamental processes that support these metabolisms may already exist before the Great Oxidation event, as suggested by possible biosignatures of oxygenic activity in older rocks. However, as long as large fluxes of reduced volcanic gases and easily oxidizable minerals are present at the surface, any oxygen produced is quickly consumed. On the sink side, the burial of reduced carbon and sulfur in sediments removes electrons from the Earth's surface system. When more organic matter and pyrite are buried than are later returned to the surface and oxidized, the net effect is to leave behind an equivalent amount of oxidizing power, which can appear as free oxygen in the atmosphere and as oxidized species in the ocean. Over time, several factors may act together to tip the balance. The cooling of the mantle and changes in volcanic style could reduce the flux of strongly reduced gases, making it easier for oxygen to accumulate. The growth and reorganization of continents could expand shallow marine and shelf areas where high rates of carbon burial occur, especially if nutrient supply increases in certain regions. The activity of microbial communities that link different metabolic pathways might become more efficient at separating oxidized and reduced products spatially or temporally, so that more reduced material is buried before it can be reoxidized. Because these processes act over long timescales and leave only indirect records, their relative importance is still being evaluated, and the exact sequence of events remains a topic of research. What the rocks clearly show, however, is that once atmospheric oxygen crosses a certain threshold, several feedbacks help stabilize the new state. The formation of an ozone layer in the upper atmosphere reduces the flux of harmful ultraviolet radiation to the surface, changing photochemical pathways and influencing the production and destruction of various gases. Increased oxidative weathering on land supplies, sulfate and other oxidized species to the ocean, shifting the balance of the sulfur cycle. In the ocean interior, the presence of oxygen in surface waters and along certain margins allows new redox gradients to form with oxic surface layers overlying anoxic deeper zones. This stratification leads to the replacement of some ferrous iron in surface waters with ferric oxyhydroxides and changes the way iron is transported and deposited. The deposition of classic banded iron formations, which require large amounts of dissolved ferrous iron in the ocean, declines after the main phase of the Great Oxidation Event, suggesting that the supply of ferrous iron to surface waters and its residence time in solution are reduced as oxygen levels rise. The oxygenation of the surface ocean also has implications for the nitrogen cycle because it allows more extensive nitrification and the formation of nitrate, which in turn can support different metabolic pathways. The extent to which deeper parts of the ocean become oxygenated is less immediate. Many models and geochemical proxies indicate that even after the atmosphere acquires measurable oxygen, large portions of the ocean interior remain anoxic or become stratified into oxic, anoxic, and sulfidic layers. In some Proterozoic basins, evidence points to episodes in which deep waters are not just anoxic, but also contain significant dissolved hydrogen sulfide, a condition described as euxinic. Under these conditions, iron and manganese cycles behave differently from those in fully oxygenated oceans, and trace metal distributions are distinctive. Thus, the Great Oxidation Event marks a major step in the evolution of Earth's surface environment, but does not immediately create a world that resembles the modern one. Instead, it inaugurates a long interval in which the atmosphere maintains a baseline of free oxygen, while the oceans experience complex and changing redox structures. From the standpoint of the larger Precambrian narrative, the rise of oxygen during the early Proterozoic reshapes the chemical setting in which rocks form elements, cycle, and microscopic life carries out its metabolisms. New mineral species become stable at the surface. Sedimentary environments that depend on oxidizing conditions become more widespread, and the balance of redox-sensitive elements shifts. These changes are all recorded in the layered rocks that accumulate on the growing continents and in the basins that fringe them. By focusing on these rocks and their chemical signatures, it is possible to trace how the planet moves from a world with nearly zero free oxygen to one in which oxygen becomes a persistent component of the outer system, modifying the interactions between crust, ocean, and atmosphere during the long Proterozoic eon that follows. During the Proterozoic eon, which spans from roughly 2.5 billion to a little more than 500 million years before the present Earth's solid surface continues to evolve from a mosaic of small, irregular Archean crustal blocks into larger, more coherent continental masses. The interior of the planet is cooler than in the Archean, though still hotter than today, and this gradual loss of heat affects the strength of the lithosphere and the style of tectonic processes. Basaltic magmatism at spreading centers and hotspots remains active, but the generation of extremely hot high magnesium lavas, such as komatiites, becomes rare. The continental crust built during Archean time from repeated partial melting, intrusion, and deformation now forms thick, buoyant regions underlain by strong lithospheric roots. These cratons act as stable cores around which younger crust accumulates. Their interiors preserve ancient greenstone belts and granitoid complexes, while their margins are the sites of ongoing tectonic activity, sedimentation, and magmatic addition. As mantle convection patterns slowly reorganize these, cratons do not stay fixed in place. They drift across the planet, sometimes converging and colliding to form larger land masses, and sometimes rifting apart again under the influence of upwelling mantle. The repeated assembly and breakup of such larger land masses defines what later geologists call the supercontinent cycle, and during the Proterozoic, several supercontinent scale configurations appear and then disperse. Although the exact outlines and timings are still refined, as new data emerge, many lines of evidence suggest that an early Proterozoic supercontinent, often referred to as Nuna or Columbia forms, by about 2 billion years ago, through the collision of multiple cratons. In these collisions, ocean basins close arcs and microcontinents accrete to larger blocks, and mountain belts rise where thickened crust is compressed. Deep roots of cold lithospheric mantle grow beneath the assembled continents, strengthening them further. Over time, erosion wears down the mountains and delivers large volumes of sediment to adjacent basins, building thick sequences of sandstones, shales, and carbonates along the flanks of the supercontinent. Later, in the Proterozoic, another major assembly, commonly called rodinia, brings together many of the world's cratons into a different configuration. The evidence for these supercontinents comes from several independent sources. Paleomagnetic measurements in rocks of known age record the direction and inclination of Earth's magnetic field at the time they form, allowing reconstruction of the approximate latitude and relative positions of crustal blocks through time. Matching belts of deformed and metamorphosed rocks across now distant continents indicate former collision zones where crust once joined and later separated. Patterns in the age of igneous and metamorphic events, as recorded by minerals such as zircon, show pulses of activity that line up on multiple continents, signaling widespread orogeny and magmatism during supercontinent assembly. Together, these observations support the idea that Proterozoic continents go through at least 2 major cycles of clustering and dispersal. The assembly of supercontinents has important consequences for the distribution of land and sea. When a large proportion of continental crust gathers near the equator or within one hemisphere, the other parts of the globe may be dominated by broad, deep ocean basins. The margins of supercontinents host wide continental shelves where shallow marine environments extend for hundreds of kilometers from the shoreline toward the deep ocean. On these shelves, subsidence driven by tectonic loading and thermal cooling creates long-lived accommodation space that fills with sediments. Over tens to hundreds of millions of years, Thick packages of platform deposits accumulate, often dominated by carbonates and fine clastics. These platforms can remain tectonically quiet for long intervals, allowing chemical and biological processes in the overlying water column to leave a detailed stratigraphic record. As the continents assemble, internal regions of supercontinents can become relatively dry and may host large sedimentary basins that are far from the sea. In these interior basins, rivers and winds redistribute sand and silt, forming fluvial and aeolian deposits. Weathering of exposed rocks on the supercontinent surfaces releases ions and particles that rivers transport to coastal regions, feeding deltas, estuaries, and shelf systems. The composition of these sediments and the minerals that form during weathering reflect the prevailing climate, the composition of the crust, and the chemistry of the atmosphere. For example, the increasing presence of oxidized iron minerals in soil and sediment points to an atmosphere that sustains measurable oxygen levels following the Great Oxidation Event. At the edges of supercontinents, rift systems occasionally initiate when mantle upwelling or changes in plate boundary forces stretch and thin the lithosphere. In these zones, the crust fracture subsides and is intruded by mafic magmas. Rift basins fill with sediments and volcanic rocks, preserving records of the early stages of continental breakup. When rifting progresses to full sea floor, spreading new ocean basins open and continental fragments drift apart. Passive continental margins then form along the edges of the separating continents, marked by thick, relatively undeformed sedimentary sequences that document long periods of thermal subsidence and steady sedimentation. The alternation between convergent margins during assembly and passive margins during dispersal creates a pattern of changing depositional environments through the Proterozoic. Proterozoic seas, especially those on continental shelves and in epicontinental settings, where shallow water covers interior parts of continents, play a major role in the Earth system. They are sites where large volumes of carbonate and other sediments accumulate, where chemical exchanges between ocean and atmosphere are intense, and where microscopic life flourishes. In contrast to the Archean, when many sedimentary basins are narrow and strongly influenced by nearby volcanic arcs and greenstone belts, Proterozoic basins associated with supercontinents can be broad and long-lived. This stability allows progressive layering of sediments that record changes in sea level climate and ocean chemistry in a fairly continuous way. Within these basins, alternating layers of carbonate shale and sandstone, sometimes punctuated by iron-rich or phosphatic horizons, capture shifts in the balance of sediment supply water depth and chemical saturation states. The chemistry of Proterozoic oceans reflects both the legacy of an earlier anoxic world and the evolving influence of oxygen in the atmosphere and surface waters. While the deep ocean may remain largely anoxic or stratified into oxic, anoxic, and sometimes sulfidic layers, for much of this eon, the shallow shelves and epicontinental seas that bathe the flanks and interiors of continents often have access to oxygenated surface waters. This redox structure affects where and how certain minerals form. On open shelves with oxic surface layers, iron tends to precipitate as ferric oxyhydroxides near the sediment-water interface, leading to red-colored iron-bearing deposits in some settings. In deeper or more restricted basins where bottom waters are anoxic and may become enriched in hydrogen, sulfide iron is removed as iron sulfide minerals. such as pyrite, imparting different signatures to the sediments. Trace metal distributions such as those of molybdenum, uranium, and vanadium also respond to these redox conditions and are preserved in black shales and other fine-grained deposits. By measuring the concentrations and isotopic compositions of these elements in Proterozoic strata, it is possible to reconstruct aspects of ocean redox structure and to infer how widespread certain conditions, such as sulfidized deep waters, may be at different times. The thermal state of the mantle and the configuration of continents also influence sea level through their effects on the volume of mid-ocean ridges and the shape of ocean basins. Faster spreading and hotter ridges occupy more volume and raise sea level, flooding continental interiors and expanding shallow seas. Slower spreading and cooler ridges allow ocean basins to deepen, lowering sea level and exposing more continental shelf. Supercontinent assembly and breakup can therefore drive large-scale transgressions and regressions in which the sea advances over or retreats from continental interiors. The sedimentary record of the Proterozoic preserves many such cycles, often in the form of repeated upward shallowing or deepening sequences in shelf deposits. These changes in water depth and shoreline position, together with regional tectonic subsidence or uplift, modulate the environments available for sediment accumulation and for the activity of microbial communities in shallow waters. Overprinting these slow tectonic and eustatic changes are variations in climate that shift on time scales from millions to hundreds of millions of years. Continental configurations affect how solar energy is distributed, how ocean currents flow, and how moisture is transported. When large land masses occupy equatorial regions, intense solar heating of continents can drive strong monsoon systems that deliver heavy rainfall to certain margins while leaving interiors arid. When continents cluster at high latitudes, ice sheets can grow on land and influence albedo and ocean circulation. These broad patterns, combined with changes in greenhouse gas levels and solar luminosity, create a range of climate states during the Proterozoic. The sediments deposited on continental margins and in interior basins record these shifts through changes in facies, grain size, and mineralogy. For example, glacial deposits such as diamictites and dropstone-bearing layers indicate times when ice reaches down to lower latitudes, while thick carbonate successions and evaporates point to warmer or more arid intervals. Throughout this eon, the long-lived shallow seas that flank continents remain an important focus of interaction between the solid earth and the fluid envelopes. They are where weathering products from land enter the ocean, where carbon is fixed into carbonates and organic matter, and where elements such as phosphorus and trace metals are redistributed between water and sediment. Because these environments are often broad, sunlit, and relatively stable, they are also favorable locations for the development and maintenance of extensive microbial communities and later more complex life forms. Their sediments, accumulating over hundreds of millions of years, provide some of the best continuous records of how the Earth system responds to changes in tectonic configuration, mantle, heat flow, and atmospheric composition. From the perspective of the wider Precambrian narrative, the Proterozoic arrangement of continents, supercontinents, and seas defines the physical template on which subsequent events unfold. The positions of land masses at different latitudes control where ice can form and where intense weathering occurs. The breadth and depth of continental shelves influence how nutrients are cycled and where large amounts of carbonate and organic carbon can be buried. The opening and closing of ocean gateways redirect currents and alter the distribution of temperature and salinity in the global ocean. All of these factors set the stage for later changes in climate and in the structure of the biosphere, while remaining firmly anchored in the behavior of plates, basins, and shorelines that can be read from the rocks of Proterozoic age on the ancient cores of continents today. During the Proterozoic eon, Earth's climate system operates under boundary conditions that differ from both the earlier Archean world and the later Phanerozoic. Yet it still follows the same physical rules that govern the balance of incoming and outgoing energy. The sun is dimmer than today, but brighter than in the Archean. Volcanic outgassing and weathering regulate greenhouse gas levels, and the arrangement of continents and oceans evolves as supercontinents assemble and break apart. These factors, together with the gradually rising background level of atmospheric oxygen, give rise to long intervals of relatively stable conditions, as well as episodes of more extreme change. Among the most striking of these changes in the Proterozoic are glacial events that extend ice to low latitudes and may in some cases cover much of the planet's surface. Geological evidence from multiple continents documents these episodes and shows that the climate system can move into states markedly different from those of the present. Outside such extremes, Proterozoic climate is often described as moderate, meaning that large parts of the surface remain free of permanent ice at low and mid-latitudes and support long-lived shallow seas. The level of carbon dioxide in the atmosphere is likely higher on average than in the present day. Because the sun's luminosity is lower and stronger, greenhouse forcing is needed to maintain above freezing temperatures over much of the globe. Continental positions also matter. When supercontinents cluster near the equator, high elevation land under warm, wet conditions can experience intense chemical weathering, drawing down carbon dioxide over long time scales. When large land masses straddle higher latitudes, snow and ice can accumulate more easily on their surfaces, increasing planetary albedo and promoting cooler climates. Sedimentary rocks of Proterozoic age record this variability. Changes in the types of carbonates and clastics deposited on continental shelves, the presence or absence of evaporites and glacial deposits, and variations in stable isotope ratios of oxygen and carbon all point to shifts in temperature, precipitation, and ocean chemistry. Among these signals, a small number of intervals stand out because they preserve evidence for very extensive glaciation. In rocks of Neoproterozoic age, roughly between 800 and 600 million years before the present, glacial deposits occur on multiple continents. At paleolatitudes that, based on paleomagnetic data, lie close to the equator at the time of deposition. These deposits include diamictites, which are poorly sorted, conglomeratic rocks containing a wide range of clast sizes and are commonly interpreted as ancient till or debris flows associated with ice. In some cases, lonestones lie within fine-grained marine sediments, where isolated large clasts appear to have been dropped from floating ice into quiet water. Overlying these glacial deposits in many sequences are distinctive layers of carbonate rock known as cap carbonates. These carbonates show sedimentary features consistent with rapid precipitation in shallow marine settings, and their carbon isotope compositions often display large negative excursions relative to background values. the close association of low-latitude glacial deposits and cap carbonates on different continents has led to the idea that at least some Neoproterozoic glaciations involve very extensive ice cover, possibly reaching the tropics and spanning entire ocean basins. In the most extreme versions of this hypothesis, sea ice covers nearly the entire ocean, and thick ice sheets extend across continents down to low latitudes. Under such conditions, planetary albedo is high. A large fraction of incoming solar radiation is reflected back to space, and the surface remains very cold. Models show that once ice advances far enough toward the equator, the increased reflectivity can create a positive feedback that locks the climate into a globally glaciated state until some other process changes the energy balance. Volcanic outgassing continues during such an interval, adding carbon dioxide to the atmosphere, while weathering, which normally removes carbon dioxide, is greatly reduced because land surfaces are largely ice-covered and precipitation is limited. Over millions of years, carbon dioxide can therefore build up in the atmosphere to levels far higher than those of non-glacial periods. Eventually, the enhanced greenhouse effect becomes strong enough to overcome the high albedo of the ice-covered surface, and the climate system undergoes rapid warming. In this view, the transition out of a snowball state leads to intense melting, high rates of evaporation and precipitation, and strongly enhanced weathering of freshly exposed rock as ice retreats. The resulting influx of ions to the ocean, combined with high atmospheric carbon dioxide, can drive rapid carbonate precipitation, producing the observed cap carbonate sequences. Although the basic physical mechanisms behind such states are well understood, the extent and exact configuration of Neoproterozoic glaciations remain subjects of investigation. Some studies favor variants in which equatorial open water belts persist, creating so-called slush ball conditions, rather than a completely frozen ocean. In these scenarios, sea ice covers large areas, but dynamic processes maintain regions of thinner ice or open water where heat and gases can still be exchanged between ocean and atmosphere. Regardless of the exact spatial extent of ice, these Neoproterozoic glacial intervals are clearly more intense and widespread than typical Phanerozoic ice ages. They are also not the only glacial events of the Proterozoic. Earlier in the eon, there is evidence for Paleoproterozoic glaciations near the time of the Great Oxidation Event, including deposits with low-latitude indicators on some continents. Their occurrence suggests that under certain combinations of greenhouse gas levels, continental positions, and solar input, the climate system can reach very extensive glacial states more than once. Between these episodes, Proterozoic climates stabilize in configurations where ice is restricted to higher latitudes or high elevations, and where shallow seas at lower latitudes remain ice-free for long intervals. Within this framework, sedimentary rocks that accumulate on continental shelves and in interior basins during Proterozoic time record alternations between warm intervals with extensive carbonate deposition, more arid periods with evaporites, and glacial intervals with diamictites and dropstones. Associated isotope records of carbon, oxygen, and other elements capture changes in global carbon cycling temperature and redox structure of the ocean. Taken together, this evidence shows that even in a world without land, plants, and complex animals, the climate system is dynamic and capable of both long-term stability and abrupt transitions to very different states. By the middle and later parts of the Proterozoic eon, the physical and chemical environment of Earth's surface supports a biosphere that is no longer composed only of simple prokaryotic cells. New types of organisms appear that have more complex internal structure, including a defined nucleus and other organelles enclosed by membranes. These organisms are referred to as eukaryotes, and although their soft tissues almost never preserve directly, their presence is recorded through a combination of fossil shapes, microscopic structures, and organic molecules that survive in sediments. The emergence and spread of eukaryotes mark an important change in how life interacts with the Precambrian world, because cells with internal compartments can support new ways of processing energy and building larger bodies from cooperating units. The earliest signals that resemble eukaryotic life come from both body fossils and chemical remnants. In Mesoproterozoic strata, the fossil record becomes richer in forms that show features consistent with eukaryotic cells. These include acritarchs, a broad category of organic walled microfossils that are generally spherical or ornamented vesicles preserved in shales and other fine-grained sediments. Some acritarchs are large compared with typical bacterial cells and display complex wall structures, spines, or processes that suggest a capacity for more elaborate life cycles. In addition to their size and morphology, certain chemical compounds found in Proterozoic rocks support the presence of eukaryotes. These compounds, known as steranes, are derived from sterols, which are important components of eukaryotic cell membranes. When sediments that contain eukaryotic organic matter are buried and heated, the original sterols are transformed into steranes that can be extracted and identified. Findings of such molecules in rocks older than 1 billion years indicate that eukaryotic organisms, including likely algae, inhabit marine environments by that time. As the Neoproterozoic approaches, the diversity and complexity of eukaryotic fossils increase. In some basins, two-dimensional compressions of multicellular algae are preserved, showing organized filaments and blades. One example, Bongiomorpha, appears in rocks about 1 billion years old and resembles modern red algae in its overall structure. Its fossils show repeated patterns of cell division and differentiated parts that suggest simple reproductive specialization. Filamentous and sheet-like fossils in other localities, preserved as carbonaceous compressions, indicate that macroscopic photosynthetic organisms grow on or near the seafloor and in shallow water columns. These organisms do not yet form forests or reefs, but they add new textures and scales to the existing microbial mats and sediments. Simple multicellularity, where groups of cells remain attached after division and coordinate to some degree, arises in several eukaryotic lineages during the Proterozoic. In many cases, the resulting organisms are small and thin, such as filament mats or hollow spheres. Fossils of colonial and multicellular forms occur as clusters of similarly sized cells arranged in chains, plates, or masses, sometimes with evidence for a surrounding envelope. The advantages of multicellularity in these environments likely include increased size relative to single-celled predators or grazers and more efficient exploitation of light and nutrients in stratified water columns. Microfossils assigned to probable heterotrophic eukaryotes also appear. Some large ornamented acritarchs may represent resting cysts of planktonic protists. Their robust walls and complex surface features suggest life cycles that include dispersal and survival stages adapted to variable conditions in the water column. The presence of such planktonic eukaryotes implies a food web in which small photosynthetic cells, bacteria, and dissolved organic matter support larger microbial predators and recyclers. This added complexity influences how carbon and nutrients move through the ocean because eukaryotic plankton often have different sinking rates and feeding strategies than purely prokaryotic communities. The relationship between eukaryotic evolution and environmental change during the Proterozoic is an area of active research. Rising oxygen levels in surface waters after the Great Oxidation Event may create niches where larger cells with higher energy demands can thrive, because mitochondria in eukaryotic cells use oxygen to generate energy efficiently. At the same time, the structure of Proterozoic oceans with oxic surface layers and more reducing deeper waters provides a range of habitats where different metabolic strategies can coexist. Eukaryotic algae likely occupy sunlit zones of the ocean, contributing to primary production and influencing the composition of organic matter that sinks into deeper layers. Heterotrophic eukaryotes inhabit both planktonic and benthic settings, feeding on bacteria, other protists, and detritus. In shallow marine environments, on continental shelves and platforms, eukaryotic algae sometimes grow in association with microbial mats, forming layered communities where photosynthetic and heterotrophic processes are closely linked. Simple multicellular forms on the seafloor may stabilize sediments and create small habitats for other microorganisms. The development of multicellularity also has implications for how organisms interact with their physical surroundings. Larger bodies experience different mechanical forces from currents and waves than individual cells do, and their growth can influence small-scale patterns of erosion and deposition. Even thin films or low mats of multicellular algae and other eukaryotes can trap and bind sediment in ways that alter the texture of the uppermost layers. As the Neoproterozoic progresses, some eukaryotic fossils reach centimeter scale or larger, and their forms become more varied. Sheets fronds and tufted aggregates appear in some assemblages, though many of these remain simple in internal organization compared with later animals and plants. Their preservation is often limited to outlines and carbonaceous films, so details of their anatomy are difficult to reconstruct. Nonetheless, their presence shows that eukaryotic life in the late Proterozoic is not confined to microscopic scales. Instead, it includes visible organisms that inhabit shallow seas and perhaps deeper slope environments, where light still penetrates. Within the time frame considered here, the main pattern is the gradual expansion of eukaryotes into diverse marine habitats, and the proliferation of simple multicellular forms alongside abundant prokaryotic communities. From the perspective of the Precambrian Earth system, this expansion adds new dimensions to the interaction between life and environment. Eukaryotic algae contribute to primary production and to the burial of organic carbon, which in turn influences atmospheric composition over long time scales. Heterotrophic protists shape microbial populations and affect how nutrients such as nitrogen and phosphorus are regenerated in the ocean. Simple multicellular organisms modify the physical structure of sediments and provide new surfaces and interfaces for chemical exchange. Together, these changes do not yet transform the planet into a world dominated by large, complex organisms, but they do mark a clear shift from an exclusively microbial biosphere toward one that also includes cells with internal complexity and coordinated multicellular bodies in the Proterozoic seas. In the latest part of the Precambrian, during the Ediacaran period, the physical and chemical setting of Earth's surface approaches the boundary that later geologists draw between the Precambrian and the Phanerozoic. Continents are assembled so that substantial land area lies in some low-latitude regions, and broad continental shelves extend outward into shallow seas. The climate following earlier Neoproterozoic glaciations settles for long intervals into states in which low and mid-latitude oceans are free of persistent sea ice and support extensive shallow water environments. Atmospheric oxygen levels are higher than in the Archean and early Proterozoic, although they still may not reach modern values, and the surface ocean generally contains dissolved oxygen in its upper layers. Deeper parts of the ocean, especially in restricted basins, can remain anoxic or even sulfidic, but the presence of oxic surface waters over wide shelf regions creates new combinations of redox conditions in the water column and sediments. On the sea floor of these shelves and slopes, sediments accumulate in patterns that reflect both physical processes and the activity of living communities. Fine silts and muds settle from suspension in quiet water, while storms and gravity-driven flows move coarser material downslope and spread it across deeper areas. Thin beds of sand or silt alternate with mudstones, and in some settings with thin limestones or dolostones. Ripple marks cross bedding and grading record the action of currents and storms, while softer sediment deformation structures indicate occasional rapid loading or slumping. Microbial mats continue to form on many surfaces in shallow to moderately deep water, stabilizing the uppermost layers of sediment and creating cohesive skins that respond to currents and waves. Where such mats cover the seafloor, they can trap fine particles and influence how later sedimentary layers preserve traces of life. Within this framework, the fossil record of the Ediacaran reveals a range of soft-bodied organisms, whose bodies are preserved mainly as impressions or reliefs on bedding planes. In several regions around the world, fine-grained sandstones and siltstones contain assemblages of such impressions that occur on surfaces interpreted as former seafloors or as event beds rapidly blanketing earlier communities. The organisms represented have varied shapes. Some are frond-like forms with branching or quilted elements arranged along a central axis. Others are discoidal or oval impressions with radial or concentric relief. Still others are elongated or ribbed forms that lie parallel or gently curved across the bedding. Many of these fossils lack obvious hard parts, internal skeletons, or clear segmental organization, and their exact biological affinities remain uncertain, but their consistent morphologies and repeated occurrence indicate that they represent organized multicellular bodies rather than random sedimentary structures. The distribution of these forms on bedding surfaces suggests that they inhabit specific environments and sometimes form dense communities. In some localities, frond-like fossils occur in clusters with individuals of different size classes preserved on the same surface. The orientation of fronds can show preferred directions reflecting alignment by currents during life or burial. Discoidal impressions may be scattered or arranged in more closely packed groups, and in some cases, overlapping relationships indicate that organisms grow or settle in proximity to one another. The absence of deep burrows in many Ediacaran beds combined with the presence of well-preserved sedimentary structures such as ripples, suggests that the sea floor in these settings is not extensively churned by mobile sediment-feeding organisms, and that the main modification of the substrate comes from microbial mats and the settlement of these soft-bodied forms. Chemical conditions at the sediment-water interface during Ediacaran time vary with depth and location, but are influenced by the presence of oxygen in overlying waters. In shallow and mid-depth shelf settings where bottom waters are oxic, the uppermost sediments contain oxidized iron and other elements, and redox gradients extend downward over centimeter to decimeter scales into more reducing zones. Within these shallow layers, microbial communities carry out metabolisms, including respiration of organic matter using oxygen nitrate or sulfate as electron acceptors. The balance between organic matter supply from overlying waters and the rate of its degradation controls how deep oxygen penetrates into the sediment and how much hydrogen sulfide accumulates below. In deeper basins or along slopes where bottom waters are poorly ventilated, the sediment surface may be anoxic and sulfidic conditions can extend upward into the water column. In such settings, only organisms tolerant of low oxygen or capable of anaerobic metabolisms can inhabit the sediment surface. The distribution of Ediacaran body fossils, together with trace fossils that record the movements of simple animals, indicates that many of the preserved communities occupy environments with at least episodic oxygenation at the sea floor. Trace fossils from the latest Precambrian provide additional information about how organisms interact with the substrate. In earlier Precambrian sediments, traces are mostly limited to simple surface trails and shallow, small-diameter burrows. In Ediacaran rocks, slightly more complex patterns appear. These include sinuous or looping trails that penetrate shallowly into the sediment's small branching structures and textures that suggest systematic probing or grazing of the uppermost layers. The depth and complexity of these traces remain modest compared with those that appear later in the record, and the overall character of the seafloor in many Ediacaran communities is still dominated by undisturbed or mat-bound sediment. Nonetheless, the presence of such traces indicates that some organisms are capable of controlled movement and interaction with the substrate beyond simple attachment. The late Precambrian seafloor thus supports a mixture of physical structures, chemical gradients, and biological communities near the transition between eons. Broad shelves and slopes that fringe continents host layered sediments shaped by storms, currents, and gravity flows. Microbial mats extend across many surfaces, binding grains and forming cohesive films. Soft-bodied multicellular organisms of various forms occupy patches within this landscape attached to the seafloor or lying upon it. Simple movers create shallow traces that record their passage within or on top of the sediment. Overlying waters carry suspended particles and dissolved substances, exchange gases with the atmosphere, and experience variations in temperature and chemistry. Deeper basins retain more reducing conditions and accumulate fine-grained deposits that record changes in ocean redox structure and productivity. In this state, just before the formal boundary used to mark the end of the Precambrian Earth's oceans and sea floors, are structured oxygen-influenced systems in which microbial and multicellular communities together shape the character of sediments and the chemical signals preserved in the rocks.